Welcome back to Space Historian. Today, we're embarking on a journey through one of the most ambitious and technically challenging aerospace research programs of the modern era. It's a story that spans more than a decade, involves some of the brightest minds in aeronautical engineering, and tackles a problem that had vexed researchers since the dawn of supersonic flight: the sonic boom. This is the story of NASA's high-speed research program and the relentless pursuit to make supersonic passenger flight over land a reality. The sound of a sonic boom is unmistakable. That sharp crack, like thunder concentrated into a single moment, represents the collision of human ambition with the laws of physics. When an aircraft exceeds the speed of sound, it creates shock waves that merge into an N-shaped pressure signature. By the time this signature reaches the ground, it manifests as that distinctive double boom, startling people, rattling windows, and making supersonic flight over populated areas essentially impossible under existing regulations. For decades, this acoustic barrier proved just as formidable as breaking the sound barrier itself had been. By the time we reached the 1980s, the dreams of widespread supersonic passenger travel had largely faded. The Concorde, that beautiful Anglo-French marvel of engineering, was flying profitable routes across the Atlantic, but it was restricted to oceanic corridors. Over land, it had to slow to subsonic speeds, negating much of its advantage. The American supersonic transport program had been cancelled in the early 1970s, a victim of environmental concerns, political pressures, and economic realities. The sonic boom, more than any other single factor, had grounded those ambitions. But the dream never truly died. Throughout the 1970s and into the 1980s, researchers at NASA's Langley Research Center and elsewhere continued to chip away at the problem. They refined theories, conducted small-scale experiments, and gradually built up a body of knowledge about how shock waves form, propagate, and might potentially be controlled. The field of sonic boom minimization had matured from wild speculation into rigorous science, even if practical applications remained elusive. The foundation years, building knowledge through the 1980s. The story of the 1990s sonic boom research renaissance doesn't begin in 1990. It begins in the early 1980s, during a period when military aviation provided the primary impetus for continued sonic boom research. In 1981, the United States Air Force initiated a comprehensive program called the Noise and Sonic Boom Impact Technology Program, mercifully shortened to NSBIT. This wasn't driven by dreams of commercial supersonic flight, but by the practical needs of military training operations. Fighter jets regularly broke the sound barrier during training exercises. Air combat training ranges across the American West regularly subjected nearby communities to sonic booms. Environmental impact statements were required. Noise complaints had to be addressed. The Air Force needed to understand sonic booms not to eliminate them, but to better predict them, measure them, and assess their impacts on structures, wildlife, and human communities. Although NASA wasn't intimately involved with NSBIT as a direct participant, the agency's expertise was invaluable. Dominic Maglieri, one of the pioneers of sonic boom research at Langley, was approaching retirement. Together with Harvey Hubbard, another Langley veteran, Maglieri compiled a comprehensive annotated bibliography of sonic boom research. This wasn't just a list of papers. It was organized into 10 major subject areas, creating a roadmap of knowledge for NSBIT participants and future researchers. It represented decades of accumulated wisdom, ensuring that hard-won insights wouldn't be lost as one generation of researchers gave way to the next. The NSBIT program achieved several noteworthy milestones. In the summer of 1987, the Air Force conducted extensive flight testing at Edwards Air Force Base in California. They flew a variety of supersonic aircraft over a large array of newly developed sensors, systematically building what would become known as boom file, a detailed sonic boom database on US supersonic aircraft. The sensors themselves represented a significant technological advance. Called Boom Event Analyzer Recorders, or BEARs, these unattended devices could capture the full sonic boom waveform in digital format. Earlier sonic boom measurements had relied on analog instrumentation with various limitations. The BEARs provided unprecedented fidelity in recording the complex pressure signatures of real-world sonic booms. The NSBIT program continued throughout the decade, making additional contributions to sonic boom science. Researchers conducted long-term monitoring of air combat training areas, tracking how sonic booms affected these regions over extended periods. They continued assessing the effects of sonic booms on structures, a concern dating back to the Oklahoma City tests of the 1960s. New studies examined impacts on livestock and wildlife, filling gaps in understanding about how animals responded to these sudden acoustic events. One particular area of focus was focused booms, sometimes called superbooms. These occurred when maneuvering aircraft, particularly during combat training, concentrated sonic boom energy in particular locations. A fighter jet pulling into a tight turn could focus its shockwaves like a magnifying glass, concentrating sunlight, creating overpressures significantly higher than those from straight and level flight. This phenomenon had been understood theoretically since the 1950s, but NSBIT provided opportunities to study it systematically. Harry Carlson at NASA Langley had developed a simplified boom prediction program that worked well for straight and level flight. In 1987, the Air Force Human Systems Division at Wright-Patterson Air Force Base in Ohio attempted to supplement this with a companion program called PC Boom, specifically designed to predict focused booms. The development of PC Boom involved adapting ray tracing routines from a proposed mainframe computer program called Boomap 2, modifying them to run on the basic desktop computers of the late 1980s. Both programs traced their lineage back to earlier work by Albion D. Taylor, who had developed a program called TRAPS, which stood for Tracing Rays and Aging Pressure Signatures. Taylor had adapted an earlier code called ARAP to account for caustics and focused booms. Kenneth Plotkin, who would become a key figure in sonic boom research, later used the waveform parameter code developed by Charles Thomas at NASA's Ames Research Center to create PC Boom 3, which became widely used in the field. In one particularly interesting application of sonic boom focusing technology that had first been envisioned back in the 1950s, fighter pilots were actually trained to deliberately lay down superbooms at specified locations. This might sound like an aggressive act, and in a sense it was, but it demonstrated a level of control over sonic boom phenomena that would have been unthinkable a few decades earlier. If pilots could be trained to focus booms, perhaps aircraft could eventually be designed to defocus them. A new dawn, the high-speed civil transport concept emerges. By the mid-1980s, the global economic landscape was shifting in ways that would profoundly affect aviation. The growing economic importance of nations in Asia was drawing attention to a simple geographic reality. The Pacific Ocean is vast. Flight times from North America to Asia were long and would remain so at subsonic speeds. Similarly, flights from Europe to most Asian destinations consumed many hours. For business travelers and the wealthy, time had value. The market potential for faster trans-Pacific and Europe to Asia travel seemed substantial. Meanwhile, in the United States, political winds were shifting. The Reagan administration, initially skeptical of government funding for civilian aeronautical research, was reversing course in the face of growing competition from Europe and Japan in high-technology exports. American aviation supremacy, which had seemed unassailable for decades, suddenly appeared vulnerable. European nations had collaborated to produce the Concorde and were developing the Airbus family of aircraft. Japan was making noises about entering the commercial aircraft market. The White House began to view aeronautical research as a strategic investment. In March 1985, the Office of Science and Technology released a report titled National Aeronautical R&D Goals: Technology for America's Future. Among its recommendations was renewed support for a long-range supersonic transport. This wasn't just nostalgia for the cancelled SST program of the early 1970s. It was a strategic vision of American technological leadership extending into the 21st century. Then, in his State of Union address in January 1986, President Ronald Reagan captured the public imagination with a bold vision. He spoke of an Orient Express that could travel from Washington to Tokyo in 2 hours. He wasn't talking about a conventional supersonic transport. He was describing a hypersonic transport, a national aerospace plane that would operate at the boundary between aeronautics and astronautics. The acronym NAS would soon become familiar to aerospace engineers across the country. In April 1986, the Battelle Memorial Institute established the Center for High-Speed Commercial Flight. This center became a focal point and influential advocate for high-speed passenger aircraft development. It brought together experts from industry, academia, and government to explore the possibilities and challenges of supersonic and hypersonic flight. Behind the scenes, NASA had been working with the Defense Advanced Research Projects Agency on hypersonic technology that would feed into the NASP concept since the early 1980s. In February 1987, the Office of Science and Technology issued an updated report on national aeronautical R&D goals, this one subtitled Agenda for Achievement. It laid out an 8-point strategy for sustaining American leadership in aviation. The report called for aggressively pursuing the NASP while also developing the fundamental technology, design, and business foundation for a long-range supersonic transport. In response, NASA accelerated its hypersonic research and began a rejuvenated effort to develop commercially viable supersonic technology. In October 1986, the agency awarded contracts to Boeing and Douglas aircraft companies for market and feasibility studies. The aircraft that emerged from these studies was now being called the High-Speed Civil Transport, or HSCT. Several internal NASA assessments accompanied the contractor studies, creating a comprehensive picture of possibilities and challenges. The studies quickly ruled out hypersonic speeds of Mach 5 and above as impractical for passenger service. The technological challenges, operational complexities, and cost considerations were simply too daunting for a near-term commercial aircraft. After considering cruise speeds ranging from Mach 1.8 to Mach 3.2, NASA and its industry partners settled on a relatively modest Mach 2.4. This speed, only marginally faster than the Concorde's Mach 2.0, would allow the use of conventional jet fuel rather than requiring exotic alternatives. The HSCT was envisioned as a significant advance over the Concorde. It would double the Concorde's range and carry 3 times as many passengers, approximately 300 in total. It would cross the Atlantic or Pacific in half the time of subsonic aircraft, transforming transcontinental and transoceanic travel. The high-risk single-stage-to-orbit NASP survived until 1994 as an experimental program designated the X-30. Its sonic boom potential was studied by current and former NASA and Air Force specialists, though the program never reached the flight test stage. The NASP represented thinking beyond even supersonic flight, but its challenges proved insurmountable with 1990s technology. The contractual studies on the HSCT emphasized a critical reality. Environmental issues had to be resolved before economically viable long-distance supersonic passenger service could become reality. Chief among these environmental concerns was the restriction on cruising over land because of sonic booms. Without the ability to fly supersonic over land masses, the HSCT's route network would be severely limited, potentially undermining its economic viability. The 1988 workshop, taking stock of sonic boom knowledge. As a first step toward addressing the sonic boom challenge, NASA Langley hosted a workshop on the status of sonic boom physics, methodology, and understanding on January 19th and 20, 1988. The workshop was coordinated by Christine Darden, an aerospace engineer who had been working on sonic boom problems at Langley since 1973. Darden's role in organizing this workshop reflected her growing prominence in the field. She was one of the relatively few researchers who had remained actively involved in sonic boom minimization ever since the demise of the Supersonic Cruise Research Program. 60 representatives from government, academia, and industry attended the workshop. Many had been involved in the earlier SST and SCR efforts. Several came from the Air Force's NSBIT program. This gathering represented much of the accumulated expertise on sonic boom phenomena in the United States. The workshop was organized into working groups focused on different aspects of the sonic boom problem. Wallace Hayes from Princeton University led a working group on theory. Albert George from Cornell University led one on minimization. Alan D. Pierce from Pennsylvania State University led a group on atmospheric effects. Clemens A. Powell from Langley led a group on human response. These four areas, theory, minimization, atmospheric effects, and human response, would structure much of the sonic boom research throughout the high-speed research program. Panels of experts from each working group identified areas most in need of additional research. Their list included boom carpets, the patterns of sonic booms that aircraft created on the ground. Focused booms required better understanding. High Mach number predictions needed improvement. Atmospheric effects, particularly how weather conditions affected sonic boom propagation, remained poorly understood. Acceptability metrics, the ways of quantifying how people responded to sonic booms, needed refinement. Signature prediction, the ability to forecast what sonic boom signature a particular aircraft design would produce, required advancement. And most fundamentally, low-boom airframe designs needed to be developed and validated. The report from this workshop served as a baseline on the latest knowledge about sonic booms and the challenges ahead. As regards aerodynamics, the workshop recognized a fundamental problem that had plagued earlier efforts. This was the high drag paradox. Simple physics suggested that aircraft designed to minimize sonic booms would suffer from increased drag, reducing their fuel efficiency and economic viability. This paradox would have to be resolved before a supersonic transport could be both quiet and efficient. Without solving this problem, low-boom designs would remain laboratory curiosities rather than practical aircraft. Phase 1, the high-speed research program launches. While Boeing and Douglas were reporting on early phases of their HSCT studies, Congress approved an ambitious new high-speed research program in NASA's budget for fiscal year 1990. This effort envisioned government and industry sharing costs, with NASA taking the lead for the first several years and industry expanding its role as research progressed. The HSR program was structured into two phases. Phase 1, scheduled from 1990 to 1995, would focus on environmental issues, engine emissions, noise around airports, and sonic booms, accompanied by preliminary design work. Among the specific objectives of Phase 1 were predicting HSCT sonic boom signatures, determining feasible reduction levels, and finding a scientific basis for setting acceptability criteria. Only after making sufficient progress on environmental problems would Phase 2 begin, ramping up in 1994. With more industry participation and greater funding, Phase 2 would focus on economically realistic airframe and propulsion technologies, ideally extending until 2001. Because much of the work involved sensitive and proprietary information, NASA implemented a limited distribution system for HSR program materials. Industry partners were understandably protective of design concepts that might provide competitive advantages. Much of the technical work done during the HSR program remains protected even decades later, never having entered the public domain fully. The aircraft companies were making progress on lower boom concepts for the HSCT, but they identified the need for more sonic boom research by NASA. Public acceptability and minimization techniques required deeper investigation before they could design a practical HSCT quiet enough to cruise over land without unacceptable performance penalties. NASA convened its first workshop for the entire high-speed research program in Williamsburg, Virginia, from May 14 to 16, 1991. Because of the sensitivity and proprietary nature of much of the information, attendance was by invitation only. 13 separate sessions covered every aspect of high-speed flight. 86 papers were presented, subsequently published with limited distribution. Robert Anderson from NASA's Aeronautics Directorate opened the meeting with a market assessment. He noted that the market for an environmentally acceptable, technically feasible, and economically viable HSCT might be as high as 300,000 passengers per day by the year 2000. This was an enormous potential market, representing billions of dollars in aircraft sales and operations. But Anderson also offered a cautionary reminder, quoting from work by Ed McLean that had examined previous programs. The quote captured the essential challenge. There would be little room for design compromises in developing a successful SST. Meeting the stringent environmental constraints of noise, sonic boom, and pollution in a safe, economically competitive SST would require the best possible combination of aerodynamic, structural, and propulsion technologies, all integrated into a congruent airplane that met all mission requirements. A NASA headquarters status report at the workshop specifically warned that the importance of reducing sonic boom could not be overstated. The stakes for the HSCT were indeed high. One Douglas study had projected that even by 2010, overwater-only routes would account for just 28% of long-range air traffic. But with supersonic overland cruise capability, the proposed HSCT could capture up to 70% of all such travel. The difference between overwater-only operations and overland capability represented hundreds of potential aircraft sales, and the difference between a marginally viable and a highly profitable program. Yet despite widespread agreement on the inherent advantages of a low-boom airliner, NASA's detailed program management flowcharts included periodic decision points on whether or not to continue including sonic boom minimization as an essential criterion for HSR designs. Based on previous efforts, the program admitted that research on low-boom designs was viewed with some skepticism as to its practical application. An early assessment was clearly warranted, as evidenced by 15 of the presentations at the Williamsburg workshop. NASA, its contractors, academic grantees, and the manufacturers were already busy conducting a wide range of sonic boom research and minimization projects, including the long-postponed issue of human response. The main goals were clear: demonstrate a waveform shape that would be acceptable to the general public, prove that a viable airplane could be built to generate such a waveform, determine that such a shape would not be too badly disrupted during propagation through the atmosphere, and estimate that the economic benefit of overland supersonic flight would make up for any performance penalties imposed by a low-boom design. The computational revolution transforms sonic boom research. During the next 3 years following the Williamsburg workshop, NASA and its partners went into what can only be described as a full-court press against the sonic boom. They initiated several dozen major experiments and studies. Results were published in reports and presented at several workshops dealing solely with sonic boom phenomena. These workshops were held at Langley Research Center in February 1992, at Ames Research Center in May 1993, at Langley again in June 1994, and once more at Langley in September 1995. These meetings, like the HSR's sonic boom effort itself, were organized into 3 major areas of research. Configuration design and operations was managed by Langley's Advanced Vehicles Division. Atmospheric propagation and human acceptability were both managed by Langley's Acoustics Division. The reports from these workshops exceeded 500 pages in length and included dozens of papers on the progress or completion of various projects, experiments, and research topics. The HSR program precipitated major advances in the design of supersonic configurations, even for reduced sonic boom signatures. Many of these advances were made possible by the rapidly expanding field of computational fluid dynamics. With CFD, engineers and researchers could now use complex computational algorithms processed by supercomputers and parallel computers to calculate the nonlinear aspects of near-field shock waves, including the Navier-Stokes equations, even at high Mach numbers and angles of attack. To understand the significance of this capability, consider the limitations that had constrained earlier research. Before CFD, the nonlinear characteristics of shock waves generated by a realistic airframe involved far too many variables and permutations to calculate by conventional means. Wind tunnel testing could measure shock waves at limited distances from models. Theoretical calculations worked well for simple shapes, but broke down for complex aircraft geometries. The gap between theory and practice was substantial. CFD promised to bridge that gap. Results could be graphically displayed in mesh and grid formats that emulated 3 dimensions. Engineers could visualize shock waves forming and propagating around aircraft. They could iterate designs rapidly, testing variations that would have required months of wind tunnel model construction using traditional methods. The great progress being made was already evident at the 1991 HSR workshop session on sonic boom and aerodynamic performance. At Langley, Christine Darden, Robert Mack, and Raymond Barger were among the few researchers to remain actively involved in sonic boom minimization ever since the SCR program ended. They had recently been joined by talented new researchers, including Peter G. Cohen. With the help of a new computer program for predicting sonic booms devised by Cohen, Langley's 11-person design team applied 2 theoretical approaches and an iterative process of modifications to build 2 12-inch wind tunnel models of HSCT-size airframes, including engine nacelles. These models were intended to combine reduced sonic boom signatures with aerodynamic efficiency. One was designed for Mach 3, cruising at 65,000 feet. The other was for cruising at Mach 2 and 55,000 feet. The finished models were first tested during October 1990 in the 9-foot by 7-foot and 8-foot by 7-foot supersonic sections of the Ames Research Center's Unitary Plan Wind Tunnel. This very busy facility was one of NASA's premier supersonic testing capabilities. The testing allowed pressure measurements out to between 5 and 6 body lengths from the models. With extrapolations confirmed for closer distances, the team was then able to use the much tighter confines of Langley's 4-foot by 4-foot Unitary Plan Wind Tunnel for additional experiments during the next 3 months. These tests required specially made equipment. A sting, the connecting device upon which a wind tunnel model is affixed, had to be designed specifically for these tests. An angle of attack mounting mechanism was developed to allow the models to be positioned precisely. The tests found excellent agreement between the forward part of the extrapolated wind tunnel measurements and the predicted sonic boom signatures. They validated the theory-derived design process, especially for the Mach 2 model. There were disappointments, however. Even using 12-inch models, the openings to the nacelles proved too small to allow sufficient airflow to pass through them during testing at Ames. The nacelles had to be removed for the testing at Langley. This limitation highlighted an ongoing challenge. Scaling effects meant that some aspects of full-size aircraft simply couldn't be tested accurately with small models. CFD capabilities. Expand from validation to design tool. The wind tunnel tests revealed limitations that pointed towards CFD as the future of sonic boom minimization research. The tests showed anomalies in the rear portions of near-field pressure signatures caused by three-dimensional flows that could not be accounted for by the axisymmetric propagation methods used in traditional analysis. They failed to reveal downstream shocks from the wings or capture the effects of exhaust plumes. CFD analysis, on the other hand, indicated that exhaust plumes might completely obscure the benefits of sonic boom shaping for Langley's Mach 3 design cruising at 60,000 feet. Traditional linear supersonic aerodynamics based on wind tunnel experimentation, along with quasi-linear acoustic propagation theory, sometimes referred to as modified linear theory, had difficulty with analysis of non-linear three-dimensional effects near the aircraft, particularly at higher Mach numbers or angles of attack. These limitations would seriously hamper designing the new HSCTs for optimum performance and low sonic booms. The Ames Research Center, with its location in the rapidly growing Silicon Valley area, had been a pioneer in applying CFD capabilities to aerodynamics. The establishment of the Numerical Aerodynamics Simulation Facility with a powerful Cray supercomputer in 1987 had positioned Ames at the forefront of computational aerodynamics. At the 1991 HSR workshop, a report by the Ames Sonic Boom team, led by Thomas Edwards and including modelling expert Samson Chung, made a bold prediction. In many ways, CFD paves the way to much more rapid progress in boom minimization. Furthermore, CFD offers fast turnaround and low cost, so high-risk concepts and perturbations to existing geometries can be investigated quickly. The Ames researchers started by validating their new CFD codes. They used three previously tested supersonic models: a cone cylinder, a rectangular wing section, and a delta-winged airframe. These simple shapes allowed direct comparison between CFD predictions and wind tunnel data. After obtaining good correlation, the Ames researchers concluded that at this point it could be said without reservation that CFD can be used in conjunction with quasi-linear extrapolation methods to predict sonic booms in the near and far field accurately. The validation experiments showed the importance of using precise airframe geometry and adequate grid resolution. Results also indicated that inviscid Euler flow analysis, which didn't require accounting for the complexities of laminar flow, was sufficient for accurate sonic boom predictions. This was an important finding because it simplified the computational requirements significantly. After validating their CFD codes, the Ames team began applying them to the two Langley models that had been tested in the Ames 9-foot by 7-foot wind tunnel. Both Ames and Langley would use the HSCT as a demonstration project for analyses on massively parallel computers under NASA's High-Performance Computing and Communications program. In a project sponsored by Christine Darden, Michael Ciclari of the Grumman Corporate Research Center at Bethpage, New York, presented results of applying a three-dimensional Euler code for multi-grid implicit marching to the two Langley HSCT models. This code was modified specifically to predict sonic boom signatures and was referred to as MIM3DSB, standing for Multi-Grid Implicit Marching in 3 Dimensions for Sonic Booms, The MIM3DSB code used a relatively simple wave drag geometry to input data. From this input, the computer calculated the propagation of shock waves from digitized replications of the models in a series of more than 100 steps, with each new step calculated from the results of prior steps. The program recorded the propagation of shock waves on three-dimensional adaptive mesh grids. These grids featured denser grid points near the aircraft where details mattered most, and a coarser adaptive grid pattern farther out where the flow was simpler. This adaptive approach allowed for faster processing while maintaining accuracy where it was needed. The shockwave data was progressively marched outward a specified distance from the airframe. From there, a waveform parameter code derived from Charles Thomas's work extrapolated the near-field signatures through atmospheric conditions to the ground. Visualizing these complex three-dimensional phenomena required sophisticated graphics. One visualization showed a side view of the grid pattern used for Langley's Mach 3 model, swept back at the approximate angle of the shock waves to save computer time compared to a more complete grid system. The Mach 3 model itself was just barely visible in the front apex of the grid system. Another visualization showed the shock waves calculated on this grid network as pressure contours, similar to how they would appear in a wind tunnel shadow graph. For visualizing the complex three-dimensional, cone-shaped expansion of shock waves, this early CFD application could display slices of the pressure waves. One particularly revealing visualization showed the computed isobars in two vertical planes aft of the Mach 2 model, clearly indicating the complexity of its flow pattern. This was something not really possible with a wind tunnel. To achieve signatures at 3 body lengths from the aircraft axis, which at supersonic speeds meant 12 to 15 body lengths downstream of the aircraft, required approximately 2 million data points. CFD and traditional methods, finding the right balance. At the 1992 Sonic Boom Workshop, Darden and Mack admitted how recent experiments at Langley had revealed limitations in using near-field wind tunnel data for extrapolating sonic boom signatures. This wasn't a defeat, but rather a maturing understanding of the appropriate uses of different research tools. During this workshop and the 2 subsequent Sonic Boom workshops, as well as at other venues, experts from Ames, Langley, and their contractors reported optimistically on the potential of new CFD computer codes to help design configurations optimized for constrained sonic booms and aerodynamic efficiency. Former Langley researcher Percy Bud Bobbitt, who had joined Dominic Maglieri at Eagle Engineering, pointed out the potential of hybrid laminar flow control for both aerodynamic and low boom purposes. This was an example of how CFD could explore synergies between different design objectives. Even the number crunching capabilities of supercomputers in the early 1990s were not yet powerful enough for CFD codes, and the grids they produced to accurately depict effects much beyond the near field. But the use of massively parallel computing held the promise of eventually being able to do so. It was becoming apparent that for most aerodynamic purposes, CFD was the design tool of the future, with wind tunnel models becoming more a means of verification. As Ames researchers had predicted in 1991, the role of the wind tunnel in low-boom model design is to benchmark progress at significant intermediate stages and at the final design point of numerical model development. By the second Sonic Boom workshop in February 1992, there were already signs of significant progress in applying CFD methods for predicting sonic boom signatures. Both Susan Cliff of Ames and Michael Ciclari of Grumman included the effects of engine nacelles in analyses of the Langley Mach 2 and Mach 3 configurations and a Boeing Mach 1.7 design. Cliff described lessons learned doing analyses with the three-dimensional Euler/Navier-Stokes aerodynamic method, known as TEAM, and a faster Euler code-based program called Airplane that relied on an unstructured tetrahedral mesh to calculate pressure signatures. These programs could model the nacelles that had defied accurate wind tunnel measurements. The ability to include engine nacelles in the analysis was crucial because these features had significant effects on the overall sonic boom signature. Ciclari followed up on his earlier work using the efficient multi-block Euler marching code MIM 3DSB with Grumman's innovative mesh technology. It was able to calculate accurate three-dimensional pressure footprints at one body length using 1.9 million grid points and extrapolate them to the ground using a linear waveform parameter method derived from Charles Thomas's work. Besides the nacelles themselves, his modelling included an engine exhaust simulation to predict the effects of the plumes on sonic boom signatures. The graphics printed out from one of these exercises demonstrated how rapidly the state-of-the-art in CFD was advancing during the early 1990s. Complex three-dimensional flow patterns, shockwave interactions, and pressure distributions could be visualized in ways that would have been impossible just a few years earlier. Among a dozen other aerodynamic papers at the 1992 workshop, Samson Chung and Thomas Edwards reported on progress in their CFD modelling using the UPS 3D parabolized Navier-Stokes code and a hyperbolic grid generation scheme for minimization purposes. They were able to improve the lift-to-drag ratio for a simplified model of Boeing's baseline low-boom HSCT configuration by almost 4%, while simultaneously extrapolating a quieter flat-top signature. To save expensive computer time, they relied on a coarse grid for their design work and only ran the end result on a fine grid to check for discrepancies. This approach, using different levels of fidelity at different stages of the design process, would become standard practice in CFD work. The sobering reality of practical design. Despite the signs of rapid progress with CFD, designing low boom characteristics into a practical airliner would not be easy. John Morgenstern described McDonnell Douglas's strategy after exploring numerous configurations. They optimized their HSCT for efficient Mach 2.4 cruising over water while having the capability to slow down to Mach 1.8 for reduced sonic boom over land. This dual-speed approach represented a compromise, accepting some performance penalty to achieve lower booms when flying over populated areas. In something of a reality check, veteran sonic boom specialist George Hagland and a Boeing colleague described analyses of their company's two low-boom designs. They recognized that lift-to-drag ratio alone was not a good measure of airplane performance. Each airplane configuration had to be evaluated in sufficient depth to determine an operating empty weight and maximum takeoff weight for a 5,000 nautical mile mission. This allowed a meaningful performance comparison to a conventional baseline configuration. Although the low-boom designs met some objectives, Hagland's team found that achieving a practical HSCT low-boom configuration with low drag, high payload, and good performance was a formidable design problem. This was the high drag paradox manifesting in real designs. Every modification to reduce sonic boom seemed to extract a penalty in aerodynamic efficiency or structural weight, or both. Documentation of the work on configuration design and analysis, presented at the Ames Sonic Boom Workshop in 1993, is not publicly available. The papers presented at the Langley Workshop in 1994 therefore represent 2 years' worth of progress, especially in applying CFD techniques. By then, results were in from an Ames experiment comparing computational fluid dynamics with traditional modified linear theory for predicting sonic boom signatures. This comparison was essential for designing HSCTs that could shape sonic boom signatures in the near, mid, and far fields. Modified linear theory was well established, fast and efficient, with an inverse design capability that allowed engineers to specify a desired signature and work backward to the required aircraft shape. But modified linear theory had trouble modelling the effects of complex geometries on pressure signatures. The limitations of CFD were not yet fully understood, but it did have the capability to do complex geometrical modeling at the cost of expensive computer time. To compare CFD with modified linear theory, the Ames Computational Aerospace branch selected a modified Boeing Arrowwing low-boom configuration as a test case. They then evaluated several CFD techniques: UPS-3D, airplane, and HFL-03, which was an Euler time relaxation code. Results contributed by Grumman with its very efficient MIM3 DSB code, and Boeing's modified linear theory techniques and ARAP-based extrapolations were included in the comparison. Although calibration problems limited the use of wind tunnel data for validation, the analysis found that all the CFD methods, although not consistent in their far-field pressure signatures, could more accurately predict the effects of lift and pitching as well as sonic booms, as measured by perceived loudness in decibels at ground level. Measuring the effects of drag, however, was highly dependent on dense grid resolution. The results indicated that CFD predictions would continue to improve with experience and better computational resources. 8 more papers at the 1994 workshop describe projects related to sonic boom minimization, most using CFD as well as wind tunnel analyses. As an example of continued wind tunnel work, Robert Mack reported some success in preventing the inlet shocks that had stymied previous experiments. He was able to obtain pressure signatures from 4 nacelles on a low-boom wind model in Langley's 4-foot by 4-foot unitary plan wind tunnel. Meanwhile, Ames and Princeton researchers reported on using CFD to design an airframe that generated a multi-shock signature that might reach the ground with a quieter sonic boom than either the ramp or flat-top waveforms that were a goal of traditional minimization theories. This represented thinking beyond the established paradigms, using CFD to explore unconventional approaches. As an excellent example of how CFD was becoming more practical as a design tool, Grumman's Michael Ciclari described how his NASA-sponsored MIM3 DSB code and numerical optimization techniques, coupled with an aerodynamic code called NPSOL, could now analyze wing body configurations in a matter of minutes rather than hours of supercomputer time. This made it efficient and economical enough to be practical as a design tool for routine use. The automated process could iterate through design variations, seeking optimal configurations that balance sonic boom reduction with aerodynamic performance. Assessing the designs: performance versus boom reduction. Even with the advances being made in designing airframes for lower sonic booms, the issue of overall performance remained a critical concern for the high-speed research program. To get a better perspective on the relationship between sonic boom acceptability and other performance requirements, an 8-person team assessed 8 of the current low-boom HSCT configurations against an unconstrained reference configuration. The team included Donald Bays and Peter Cohen from NASA Langley and former NASA intern Kathy Needleman from Lockheed Engineering and Sciences Company. Their assessment was predicated on some technologies projected to be available in 2005: advanced composite materials, aeroelastic tailoring, mixed-flow turbofan engines, and multi-purpose displays. The team evaluated such factors as lift-to-drag ratios, fuel capacity and consumption, passenger payload, takeoff distance, gross weight, and mission block time. Under these criteria, all of the low-boom designs achieved a total gross weight per passenger only slightly higher than the reference configuration. This was encouraging news, suggesting that the performance penalties of low-boom design might be manageable. But all were heavier than originally assumed and would require at least another design cycle to ensure successful low-boom shaping. The designs weren't yet mature enough to commit to production. As with studies dating back to the original SST program, the most highly swept wing planforms did not have enough lift at low speeds. This created problems for takeoff and landing, potentially requiring longer runways or higher approach speeds than would be operationally acceptable. Reinforcing previous aircraft company projections, the analysis showed that being able to fly supersonic over land areas, even on relatively short segments of routes, offered better block time and therefore economic advantages. The 8 low-boom HSCT configurations studied in this project represented the various design options being explored during Phase 1 of the high-speed research program. They ranged from highly swept delta wings to more conventional configurations with lower sweep angles. Some featured elaborate nose shaping to control the bow shock. Others relied on careful distribution of volume and lift along the fuselage to shape the overall signature. Each represented hundreds or thousands of hours of design work and analysis. Flight testing. Bridging theory and reality. Neither wind tunnels nor CFD could empirically prove the physical persistence of a shaped waveform for more than a tiny fraction of the 200 to 300 body lengths needed to represent the distance from an HSCT cruising at altitude to the surface. This credibility gap represented a significant risk. If shaped signatures didn't persist through the atmosphere, all the careful design work would be for nothing. To fill this credibility gap, Dominic Maglieri and a team at Eagle Engineering looked at various options for performing relatively economical flight tests using remotely piloted vehicles modified for low-boom characteristics. They presented this proposal at the 1991 HSR workshop. In 1992, they provided results of a feasibility study on the most cost-effective ways to verify design concepts with realistic testing. After exploring a wide range of alternatives, the team selected the Teledyne Ryan BQM-34E Firebee-2, which the Air Force and Navy had long used as a supersonic target drone. 4 of these 28-foot-long remotely piloted vehicles, which could sustain a speed of Mach 1.3 at 9,000 feet, approximately 300 body lengths from the surface, were available as surplus. Modifying them with low-boom design features such as specially configured 40-inch nose extensions could provide far-field measurements needed to verify the waveform shaping projected by CFD and wind tunnel models. The Firebee-2 was an attractive test platform for several reasons. Its modular construction meant that noses, wings, and tail surfaces could be easily swapped without major structural modifications. The vehicles had a proven track record of reliability. They could be launched from aircraft or ground-based boosters and recovered by helicopter, making them reusable. And being surplus military hardware, they were relatively inexpensive. Meanwhile, a similar but more ambitious plan at the Dryden Flight Research Center led to NASA's first significant sonic boom testing there since 1970. SR-71 program manager David Lux, atmospheric specialist L.J. Ehrenberger, aerodynamicist Timothy R. Mose, and principal investigator Edward A. Herring came up with a proposal to demonstrate CFD design concepts by having one of Dryden's SR-71S modified with a low-boom configuration. The SR-71 offered several advantages over the Little Firebee. Being much larger, faster, and higher flying, it would more closely emulate the HSCT. An SR-71 would also allow easier acquisition of near-field measurements for direct comparison with CFD predictions. The aircraft could carry instrumentation and fly with chase aircraft in ways not possible with an unmanned drone. To lay the groundwork for this modification, Dryden personnel gathered baseline data from a standard SR-71 using one of its distinctive F-16XL aircraft. The F-16XL featured a cranked arrow or double-angled delta wing planform. Built by General Dynamics in the early 1980s for evaluation by the Air Force as a long-range strike version of the short-range F-16 fighter, the elegant F-16XL had lost out to the rival McDonnell Douglas F-15E Strike Eagle, which offered even greater range and payload capability. In tests at Edwards Air Force Base during July 1993, the F-16XL, flown by Dryden test pilot Dana Purifoy, probed as close as 40 feet below and behind an SR-71 cruising at Mach 1.8 to collect near-field pressure measurements. This was demanding flying, requiring the F-16XL pilot to maintain precise position relative to the SR-71 while flying through the Blackbird's shockwaves. The F-16XL used a standard flight test nose boom fitted with pressure sensors. Langley and McDonnell Douglas analysed this data. Both reached generally favourable conclusions about the ability of high-order CFD and McDonnell Douglas's proprietary MD Boom program to serve as design tools. Kenneth Plotkin and Juliet Page of Weil Laboratories had developed MD Boom from a focus version of the Thomas code that Plotkin and a colleague developed in 1976. This focus code was also adapted for PC Boom 3, which replaced the original TRAPS-based PC Boom. Based on these results, a team led by low-boom aerodynamicist John Morgenstern at McDonnell Douglas Aerospace West designed modifications to alter the bow and middle shockwaves of the SR-71 by reshaping the front of the airframe with a nose glove and adding to the mid-fuselage cross-section. An assessment of these modifications by Lockheed Engineering and Sciences Company found them feasible. The next step would be obtaining the considerable funding needed for the modifications and testing. In May 1994, Dryden used two of its fleet of FA-18 Hornets to measure how near-field shockwaves merged, assessing the feasibility of a similar low-cost experiment in waveform shaping using two SR-71s. Flying at Mach 1.2 with one aircraft below and slightly behind the other, the first experiment positioned the canopy of the lower FA-18 in the tail shock, extending down from the upper FA-18. This was called a tail canopy formation. The second experiment had the lower FA-18 fly with its canopy in the inlet shock of the upper FA-18, called an inlet canopy formation. Ground sensor recordings revealed that the tail canopy formation caused two separate N-wave signatures, but the inlet canopy formation yielded a single modified signature, which two of the recorders measured as a flat-top waveform. This low-cost technique presented safety issues, however. Even with the excellent visibility from the FA-18's bubble canopy, one pilot used the inlet shockwave as a visual cue for positioning the aircraft and its responsive flight controls. Maintaining such precise positions was not easy. The pilots recommended against doing the same with SR-71s, considering their larger size, slower response, and limited cockpit visibility. Understanding atmospheric effects, the missing piece. Atmospheric effects had long posed many uncertainties in understanding sonic booms, but advances in acoustics and atmospheric science since the SCR program promised better results. Not only did the way air molecules absorb sound waves need to be better understood, but so did the old issue of turbulence. In addition to using the Air Force's boomfile database and other available material, Langley's acoustics division had Eagle Engineering, in a project led by Dominic Maglieri, restore and digitize data from the irreplaceable XB-70 records from the 1960s. This historic data represented measurements from the largest supersonic aircraft ever to generate sonic booms over populated areas. The Acoustics Division, assisted by Lockheed Engineering and Sciences Company, also took advantage of the NATO Joint Acoustic Propagation Experiment at the White Sands Missile Range in August 1991 to conduct new flight testing. The researchers arranged for Air Force F-15, F-111, and T-38 aircraft and one of Dryden's SR-71s to make 59 supersonic passes over an extensive array of bare and other recording systems, as well as meteorological sensors. Tests were conducted both early in the morning when the air was still and during the afternoon when there was usually more turbulence. Although meteorological data was incomplete, results later showed the effects of molecular relaxation and turbulence on both the rise time and overpressure of bow shocks. Henry Bass of the University of Mississippi, a key participant in the Joint Acoustic Propagation Experiment, was an important researcher on the acoustics of turbulence. Another academic researcher, David Blackstock of the University of Texas, and his graduate students discovered additional effects of turbulence as well as other atmospheric instabilities on sonic booms, some through innovative laboratory experiments. Starting with the first HSR workshop, NASA and NASA-sponsored researchers, such as Alan D. Pierce of Penn State University, began producing a variety of papers on waveform freezing, the term for signature persistence. They worked on measuring diffraction and distortion of sound waves and tried to ascertain the complex relationship among molecular relaxation, turbulence, humidity, and other weather conditions. For better visualizing sonic booms, Leonard Weinstein of Langley developed a way to capture stunning images of actual shock waves in the real atmosphere. He did this using a ground-based Schlieren imaging system, essentially a specially masked and filtered tracking camera with the sun providing backlighting. This technique was first demonstrated in December 1993 with a T-38 flying just over Mach 1 at Wallops Island in Virginia. The resulting photographs were remarkable, showing clearly the bow shock and tail shock from the T-38 as dark lines against the sky. These images provided visual confirmation of theoretical predictions and demonstrated that shock waves maintained their structure over significant distances. The Schlieren technique would become an important tool for future sonic boom research. The major SR-71 campaign, comprehensive data gathering. From February 1995 through April 1995, the Dryden Flight Research Center conducted more extensive SR-71 and F-16XL sonic boom flight tests. Led by Ed Haring, this experiment included an instrumented YO-3A light aircraft from Ames, an extensive array of various ground sensors, a network of new differential global positioning system receivers accurate to within 12 inches, an installation of a sophisticated new nose boom with 4 pressure sensors on the F-16XL. On 8 long missions, one of Dryden's SR-71s flew at speeds between Mach 1.25 and Mach 1.6 at altitudes from 31,000 feet to 48,000 feet. The F-16XL, kept aloft by in-flight refuelings, made numerous near-field and mid-field measurements of bow, canopy, inlet, wing and tail shock waves at distances from 80 feet to 8,000 feet. Some of these measurements showed that the canopy shock waves were still distinct from the bow shock after 4,000 to 6,000 feet. This persistence of individual shockwave features was important information for understanding how shaped signatures might evolve during propagation. Comparisons of far-field measurements obtained by the YO-3A flying at 10,000 feet above ground level and the recording devices on the surface revealed effects of atmospheric turbulence. Analysis of the data validated 2 existing sonic boom propagation codes used for predicting far-field signatures, Zephyrus and Shock-N. The results clearly showed how variations in the SR-71's gross weight, speed, and altitude and atmospheric phenomena such as molecular absorption cause differences in shockwave patterns and their coalescence into N-shaped waveforms. This innovative and successful experiment marked the end of dedicated sonic boom flight testing during the HSR program. Phase 2 testing focused on the many other issues involved in designing a practical 320-foot long, 300-passenger Mach 2.4 HSCT with a range of 5,000 nautical miles that would fly only subsonically over land. NASA's creative partnership with Russia in using a Tu-144 as a supersonic laboratory from 1996 to 1999 did not include sonic boom measurements as originally planned. The Tu-144, often called the Soviet Concorde, provided valuable data on other aspects of supersonic flight, but sonic boom research was no longer the priority it had been. The human response studies. The decisive factor. All of the research into the theoretical, aerodynamic, and atmospheric aspects of sonic booms, no matter how successful, would not protect the high-speed research program from what had been the Achilles heel of previous efforts: the subjective responses of human beings. As a result, Langley, led by Kevin Shepard of the Acoustics Division with researchers such as Brenda Sullivan, Jack Leatherwood, and David McCurdy, began a systematic effort to measure human responses to different strengths and shapes of sonic booms to help determine acceptable levels. As an early step, the division built an airtight foam-lined sonic boom simulator booth known as the Boom Box. This was derived from a similar apparatus at the University of Toronto. Using the latest in computer-generated digital amplification and loudspeaker technology, it was capable of generating shaped waveforms up to 4 pounds per square foot and 140 decibels. Based on responses from subjects, researchers selected the perceived level decibel, or PLDB, as the preferred metric for quantifying human response to sonic booms. For responses outside a laboratory setting, the NASA Langley team planned several additional acceptance studies. By 1994, early results had become available from 2 of these human response projects. Langley and Weil Laboratories had developed mobile boom simulator equipment for what was called the In-Home Noise Generation Response System, or IHONORS. It consisted of computerized sound systems installed in 33 houses for 8 weeks at a time in a network connected by modems to a monitor at Langley. From February 1993 to December 1993, these households were subjected to almost 58,500 randomly timed sonic booms of various signatures for 14 hours a day. Although definitive analyses were not available until the following year, the initial results confirmed how the level of annoyance increased whenever subjects were startled or trying to rest. This was hardly surprising, but it provided quantitative data on what had previously been subjective impressions. Preliminary results were also in from the first phase of the Western USA Sonic Boom Survey of civilians who had been exposed to such sounds for many years. This part of the survey took place in remote desert towns and settlements located around the Air Force's vast Nellis Combat Training Range complex in Nevada. Unlike previous community surveys, this study correlated citizen responses to accurately measured sonic boom signatures using bare devices in places where booms were a regular occurrence, yet where the subjects did not live on or near a military installation. This was important because the economic benefits of a base to the local economy might influence opinions of residents living near military facilities. The researchers conducted 1,042 interviews. Although findings were not yet definitive, these interviews proved more decisive than any of the many other research projects in determining the future direction of the HSCT effort. Based on a metric called day-night average noise level, the respondents found the booms much more annoying than previous studies on other types of aircraft noise, even at the levels projected for low boom designs. Their negative responses effectively dashed hopes that the HSR program might lead to an acceptable overland supersonic transport. Even the quietest boom signatures being contemplated were still too annoying for regular exposure. The dream of supersonic flight over land, which had seemed tantalizingly close just a few years earlier, was slipping away again. Phase 2: Strategic Retreat and Redirection. well before the paper on the Western USA survey was presented at the 1994 Sonic Boom Workshop. Its early findings had prompted NASA headquarters to reorient the high-speed research program toward an HSCT design that would fly supersonic only over water. Just as with the Advanced Supersonic Transport program 20 years earlier, this became the goal of Phase 2 of the HSR program. Phase 2 began with the help of fiscal year 1994 funding left over from the cancelled National Aerospace plane program. Once again, public annoyance with the sonic boom had proved too big an obstacle for even a new generation of aeronautical technology to overcome. The revamped HSR program would continue intensive supersonic research for the rest of the decade, but after Boeing's absorption of McDonnell Douglas in 1996, Boeing's continued willingness to invest in the program became crucial. At the end of the 1994 workshop, Christine Darden discussed the progress and lessons learned to date, as well as the next steps for sonic boom research. Regarding progress, she noted that tremendous advances in supercomputers, gridding schemes, and computational algorithms had allowed computational fluid dynamics to become a new tool in the prediction of near-field sonic boom signatures. Although major improvements were still needed in correlating this nonlinear data with the linear methodology used for effects in the mid and far fields, several achievements were already in evidence. These included the benefits of CFD for design concepts and analysis of near-field shockwave signatures, improved F-function analysis, and methods to predict inlet shocks, increased use of nonlinear corrections for modified linear theory techniques, minimization theories for cambered wing bodies, measurements of flow-through nacelles on wind tunnel models, and improving some performance criteria of low boom concepts to within 3% of unconstrained baseline configurations. While the lower boom design efforts had shown outstanding progress, management of this effort had not been ideal. Dispersal of the work among 2 NASA centers and 2 major aircraft manufacturers had resulted in communication problems as well as a certain amount of unhelpful competition. The milestone-driven HSR effort required concurrent progress in various technical and scientific areas, which is inherently difficult to coordinate and manage. And even if low-boom airplane designs had been improved enough to meet acoustic criteria, they would have been heavier and performed more poorly at slow speeds than unconstrained designs. Under the new HSR strategy, any continued minimization research was now aimed at lowering the sonic boom of the baseline over-water design. Propagation studies would concentrate on predicting boom carpets, focused booms, secondary booms, and ground disturbances. In view of the HSCT's overwater mission, new environmental studies would devote more attention to the potential penetration of shockwaves into water and the effects of sonic booms on the marine mammals and birds that might be affected. Concorde operations had revealed no such problems, but the HSCT would be about twice the weight, but only 50% longer than the Concorde. The sonic boom overpressures generated by the baseline designs would tend to be about 50% higher. As a result, aerodynamicists such as Robert Mack of Langley, John Morgenstern of McDonnell Douglas, George Hagland of Boeing, and Michael Ciclari of Grumman, which merged with Northrop Corporation in April 1994, turned their attention to minor modifications that could reduce this level with only minimal performance penalties. Although the preliminary results of the first phase of the Western USA survey had already had a decisive impact, while laboratories completed the second phase with a similar polling of civilians in Mojave Desert communities exposed regularly to sonic booms, mostly from Edwards Air Force Base and China Lake Naval Air Station. Surprisingly, this phase of the survey found the Californians much more amenable to sonic booms than the less tolerant desert dwellers in Nevada. But they were still more annoyed by booms than by other aircraft noise of comparable perceived loudness. With the decision to end work on a low-boom HSCT, the proposed modifications of the Firebee, remotely piloted vehicles, and SR-71 had been cancelled. This postponed for another decade the first live demonstrations of boom shaping. Nevertheless, some flight testing that would prove of future value continued to be conducted. The final workshop and program conclusion. The last of the sonic boom workshops, held at Langley in September 1995, no doubt seemed rather anticlimactic for the 46 attendees in view of the new, less ambitious HSR goals for a high-speed civil transport. As with the SST and SCR programs, however, their research, the latest of which would be published in a 2-volume compendium, added greatly to the scientific knowledge and engineering skills that would be needed if and when another effort to develop a civilian supersonic airplane might be initiated. Several papers indicated that the behavior of shock waves and acoustic rays under a wide range of atmospheric conditions were now well understood. Yet the challenges in designing a practical airplane that could exploit this knowledge to control sonic boom signatures, especially in view of the disturbing new evidence collected on the sensitivity of human responses to them, were still daunting. Even with the rapid progress with computational fluid dynamics, results so far indicated the need for much more computing power and new techniques. As Kenneth Plotkin explained, due to a combination of computational costs and numerical algorithms losing resolution after many steps, CFD cannot be brought all the way to the ground or even very many body lengths away from the aircraft. Developing a high-speed civil transport ran into other barriers besides the sonic boom. By late 1998, the HSR program confronted a combination of economic, technological, political, and budgetary problems. These included cost overruns for the International Space Station. The Boeing company, now estimating that development of the HSCT would take $13 billion, cut its support. The administration of President William J. Clinton, with the backing of NASA Administrator Daniel S. Goldin, decided to terminate the HSR program at the end of fiscal year 1999. Although other research programs picked up elements of the HSR, having to end it, and a similar program for an advanced subsonic transport deprived NASA of the focus these programs helped give to its aeronautical research. Ironically, NASA's success in helping the aircraft industry develop quieter subsonic aircraft, which had the effect of moving the goalpost for acceptable airport noise, was one of the factors convincing Boeing to drop plans for a supersonic airliner. Nevertheless, the high-speed research program was responsible for truly significant advances in technologies, techniques, and scientific knowledge, including a better understanding of the sonic boom and ways to diminish it. The computational tools developed during the HSR program would find applications in many other areas of aerospace engineering. The understanding of atmospheric effects on shockwave propagation advanced significantly. The human response data, though discouraging for supersonic transport advocates, provided a solid scientific foundation for future policy decisions. Looking toward the future, the 2001 National Research Council study. To help identify areas for future research that might overcome the barriers to supersonic flight encountered by the HSR program, NASA in 2000 asked the National Research Council to conduct a comprehensive investigation of the relevant technologies that would be needed. The Council's Aeronautics and Space Engineering Board formed an expert 14-person committee on breakthrough technologies to perform this task. Released in 2001, the committee's in-depth study focused on high-risk, high-payoff technologies where NASA research could make a difference over the next 25 years. While advising that NASA should have its eye on the grand prize of supersonic commercial transports, the committee deemed it quite appropriate for NASA to conduct sonic boom research related to supersonic business jets, which were increasingly seen as having a more realistic chance of meeting sonic boom requirements. Their study concluded with an admonition that remains relevant today. if the United States intends to maintain its supremacy in the commercial aerospace sector, it has to take a long-term perspective and channel adequate resources into research and technology development. The technological challenges to commercial supersonic flight can be overcome as long as the development of key technologies is continued. Without continued effort, an economically viable, environmentally acceptable commercial supersonic aircraft is likely to languish. Reflecting on a decade of intense research, the 1990s represented perhaps the most intensive period of sonic boom research in history. The high-speed research program brought together hundreds of researchers from NASA, industry, academia, and other government agencies. They produced thousands of pages of technical reports, dozens of experimental programs, and fundamental advances in understanding. The computational revolution transformed sonic boom research from a largely empirical field and dependent on wind tunnel testing to one where complex three-dimensional flows could be analyzed in detail before any hardware was built. The ability to visualize shock waves, to iterate through design variations rapidly, and to optimize configurations for multiple objectives simultaneously represented capabilities that earlier researchers could only dream of. Flight testing provided crucial validation of theoretical predictions and revealed the importance of atmospheric effects. The atmospheric research conducted during the HSR program advanced understanding of how turbulence, humidity, temperature gradients, and wind shear affected sonic boom propagation. The human response studies, though they delivered discouraging results, finally provided solid scientific data on a question that had been debated for decades. Perhaps most importantly, the HSR program demonstrated that low-boom aircraft designs were feasible from an engineering standpoint. The challenge was not whether aircraft could be designed to produce shaped sonic boom signatures. The challenge was whether those signatures would be quiet enough to gain public acceptance and whether the aircraft carrying them could meet performance and economic requirements. Christine Darden's leadership throughout this period exemplified the best of NASA's research culture. Her technical contributions to sonic boom minimization theory, her management of the sonic boom research effort, and her mentorship of younger researchers helped ensure that knowledge accumulated during earlier programs wasn't lost. She became the first African-American woman at Langley Research Center to reach the Senior Executive Service, the top rank in the Federal Civil Service. The researchers who participated in the HSR program's sonic boom element came from diverse backgrounds. Some, like Dominic Maglieri and Robert Mack, had been working on sonic boom problems since the 1960s. Others, like Peter Cohen and Ed Herring, represented a new generation bringing fresh perspectives and new technical skills, particularly in computational methods. The collaboration between these generations ensured continuity while enabling innovation. The technical legacy. The technical achievements of the HSR sonic boom research remain impressive even decades later. The development of efficient CFD code specifically tailored for sonic boom prediction represented a major advance. The MIM3 DSB code developed by Michael Ciclari and his colleagues at Grumman could analyze complex configurations in minutes rather than hours, making it practical as a design tool. The validation work comparing CFD predictions with wind tunnel data and flight test measurements established confidence in these computational methods. The understanding of how to shape sonic boom signatures through careful design of aircraft geometry reached a level of sophistication far beyond what had been possible during the original SST program. The concept of equivalent area distribution, relating the three-dimensional aircraft shape to the one-dimensional pressure signature at the ground, became a practical design tool rather than just a theoretical construct. The atmospheric research revealed the complexity of sonic boom propagation through the real atmosphere. The neat theoretical predictions assuming a standard atmosphere were shown to be approximations, sometimes quite rough, of what actually occurred. Turbulence could both smooth and distort signatures in ways that depended on the scale and intensity of the turbulent eddies. Temperature and humidity affected the molecular relaxation of shock waves, changing rise times and peak overpressures. The human response research, despite its discouraging results for overland supersonic flight, established a scientific basis for assessing acceptability. The IONAS system demonstrated that controlled experiments in realistic settings were possible. The Western USA survey methodology showed how to gather meaningful data from communities with long-term exposure to sonic booms. Lessons for future programs. The HSR program provided important lessons that would influence future efforts to develop quieter supersonic aircraft. The importance of addressing human response early and systematically was clearly demonstrated. Previous programs had treated human response almost as an afterthought, assuming that if technical solutions could be found, public acceptance would follow. The HSR program showed that this assumption was unwarranted. The value of integrated research combining theory, computation, wind tunnel testing, and flight testing was also clearly demonstrated. Each approach had strengths and limitations. Theory provided insight and guided thinking, but couldn't capture all the complexities. Computation was powerful but required validation. Wind tunnels provided controlled conditions but had scaling limitations. Flight testing revealed real-world complexities but was expensive and time-consuming. Using all these approaches in an integrated manner produced the best results. The management challenges of large, multi-center, multi-contractor programs became apparent. Competition between research centers and contractors sometimes hindered rather than helped progress. Better communication and coordination mechanisms were needed. Clear roles and responsibilities, regular technical interchange meetings, and integrated planning helped but didn't completely solve the coordination problems. The economic realities of commercial aircraft development also became clearer. Even if technical problems could be solved, the business case for a new aircraft had to be compelling. With development costs in the tens of billions of dollars and certification requirements becoming ever more stringent, the market had to be large and assured. The restriction to overwater operations drastically reduced the potential market for an HSCT, making it a marginal business proposition at best. The path forward. After HSR. When the HSR program ended in 1999, it didn't mark the end of sonic boom research. The knowledge and tools developed during the program would enable future efforts. In 2002, DARPA initiated the Quiet Supersonic Platform program, which would eventually lead to the Shaped Sonic Boom Demonstrator flight test using a modified F-5 in 2003. This test, conducted by Northrop Grumman, with Dominic Maglieri as a key consultant, finally demonstrated in flight that shaped signatures could persist through the atmosphere. The success of that demonstration validated the decades of work that had gone into understanding sonic boom shaping. It showed that the theories developed, the CFD tools created, and the design methods refined during the HSR program and earlier efforts actually worked in the real world. The signature measured on the ground matched predictions remarkably well. This success energized interest in quiet supersonic flight and eventually led to NASA's Low Boom Flight Demonstrator program, now embodied in the X-59 aircraft developed by Lockheed Martin. The X-59, scheduled to begin flight testing in the mid-2020s, represents the culmination of more than 60 years of sonic boom research. It incorporates design principles developed during the HSR program, uses CFD tools that trace their lineage to codes developed in the 1990s, and will be tested using methods pioneered during HSR flight experiments. The focus has shifted somewhat from large commercial transports to smaller business jets, as the National Research Council recommended. The market for supersonic business jets appears more robust than that for large supersonic airliners, at least in the near term. Several companies are developing supersonic business jet concepts, all relying on the sonic boom knowledge base built up over decades of research. The human element in technical achievement. Behind all the technical achievements, computer codes, wind tunnel tests, and flight experiments were people. Researchers who dedicated years or entire careers to solving the sonic boom problem. Technicians who built and maintained experimental equipment, pilots who flew demanding test missions, administrators who fought for funding and protected programs from cancellation as long as possible. Christine Darden's story exemplifies this human dimension. Starting as a data analyst, what NASA then called a human computer, she pushed for opportunities to work on engineering problems. Her question to a director about why men and women with the same qualifications were placed in different jobs led to her transfer to an aerospace engineering position. Her contributions to sonic boom minimization theory earned her recognition as one of NASA's preeminent experts on supersonic flight. Dominic Maglieri's career spanned from the earliest days of supersonic flight research through the HSR program and beyond. His institutional knowledge proved invaluable in ensuring that lessons from earlier programs informed later efforts. His work compiling the sonic boom bibliography, restoring historic XB-70 data, and mentoring younger researchers ensured continuity across generations. The pilots who flew the test missions faced real risks. Flying in close formation at supersonic speeds, maneuvering precisely to position instrumentation in shockwaves, maintaining position while flying through turbulent air disturbed by another aircraft's passage, all required exceptional skill and courage. The F-16XL pilots, who probed within 40 feet of an SR-71's shockwaves, the FA-18 pilots, who flew in formation with one aircraft's canopy in another's shockwave, these were not routine flights. The broader context of supersonic flight research. The sonic boom research of the 1990s existed within a broader context of supersonic flight development. The Concorde continued flying throughout this period, demonstrating daily that supersonic passenger flight was technically feasible and commercially viable on the right routes. The fact that only 20 Concordes were built and that the type was restricted to a handful of routes illustrated the limitations imposed by sonic boom regulations and operating economics. Military aviation continued to drive some aspects of supersonic aerodynamics research. Fighter aircraft regularly operated at supersonic speeds. The need to understand and predict their sonic boom impacts on training ranges and surrounding communities remained. The Air Force's NSBIT program, which had helped keep sonic boom research alive during the 1980s, continued through the 1990s. The end of the Cold War changed priorities and budgets. The peace dividend that followed the collapse of the Soviet Union meant reduced military spending. Some of this reduction fell on research programs. At the same time, the dramatic growth of commercial air travel created new opportunities and challenges. The prospect of supersonic business jets serving high-value passengers on long routes appeared increasingly attractive. Environmental consciousness was growing. The debates about supersonic transport in the early 1970s had focused heavily on potential ozone depletion and sonic boom nuisance. By the 1990s, climate change had emerged as a major concern. The fuel consumption and emissions of supersonic aircraft came under scrutiny. Noise around airports, always a sensitive issue, became even more so as airports expanded and communities grew closer to their boundaries. The international dimension. While the HSR program was primarily an American effort, supersonic research continued in other countries. European researchers maintained expertise developed during the Concorde program. Russian scientists continued work related to the Tu-144, despite that aircraft's limited operational history. Japanese researchers explored supersonic transport concepts as part of broader aerospace development efforts. The partnership between NASA and Russia in operating the Tu-144 as a flying laboratory from 1996 to 1999 represented an interesting post-Cold War collaboration. Although sonic boom measurements weren't conducted as originally envisioned, the program demonstrated that former adversaries could work together on civil aerospace research. Data gathered from the Tu-144 flights contributed to understanding of supersonic aerodynamics, propulsion, materials, and operations. International regulations on supersonic flight over land remained a barrier. Different countries had different rules, but most prohibited or severely restricted supersonic flight over their territories. The FAA rule in the United States prohibiting civil supersonic flight that creates sonic booms audible on the ground effectively blocked overland supersonic operations. Similar rules existed in Europe and elsewhere. Any future supersonic transport would need to either operate only over water or demonstrate sonic boom signatures quiet enough to gain regulatory approval for overland flight. The role of funding and political support. The rise and fall of the HSR program illustrated the crucial role of sustained funding and political support for long-term aerospace research. The program began with strong support, driven by concerns about international competitiveness and visions of American technological leadership. Annual budgets in the hundreds of millions of dollars enabled a comprehensive research effort. As the program matured and challenges became apparent, support began to erode. The decision to shift from overland-capable to overwater-only HSCT removed much of the technical challenge and some of the excitement from the program. The absorption of McDonnell Douglas by Boeing meant one less competitor and potentially less industry investment. Cost overruns on the International Space Station created pressure to find budget savings elsewhere in NASA. The decision to terminate the program at the end of fiscal year 1999 reflected multiple factors. Boeing's estimate that developing the HSCT would cost $13 billion was daunting. The company was unwilling to make that investment given the limited market for an overwater-only supersonic transport. NASA's aeronautics budget was under pressure from multiple directions. The Clinton administration, while generally supportive of aerospace research, had to make choices about priorities. Some criticized the decision to terminate HSR as short-sighted, arguing that abandoning the program wasted the investment already made and guaranteed that American leadership in supersonic flight would erode. Others argued that the program had accomplished its major technical objectives and that further investment would be better directed toward technologies with nearer-term applications. The debate reflected fundamental questions about the appropriate role of government in supporting advanced aerospace research. Technological spin-offs and applications. Although the HSR program didn't lead directly to a new supersonic transport, the research produced valuable spin-offs. The CFD codes developed for sonic boom prediction found applications in other areas of aerodynamics. The understanding of shockwave physics contributed to work on hypersonic vehicles and spacecraft re-entry. The experience with advanced composite materials and high-temperature structures influenced designs for other aircraft. The human response research, while discouraging for supersonic transport advocates, contributed to broader understanding of community noise impacts. The IONAS methodology could be adapted to study responses to other types of environmental noise. The metrics developed for quantifying sonic boom annoyance related to ongoing work on aircraft noise around airports. The flight test techniques developed during the HSR program, particularly the use of probe aircraft to measure near-field shock waves and the integration of GPS for precise positioning, found applications in other research programs. The experience gained in managing large multi-institutional research programs influence the organization of later NASA aeronautics research efforts. Conclusion: a foundation for future success. As we look back on NASA's high-speed research program and its intensive sonic boom research effort, we can see it as both an ending and a beginning. It marked the end of one dream, the vision of large supersonic airliners, routinely cruising over land masses at twice the speed of sound, carrying hundreds of passengers. The human response research made clear that sonic booms, even significantly reduced ones, were too annoying for regular exposure over populated areas. But it also marked a beginning. The program demonstrated that shaped sonic boom signatures were technically feasible. It developed the computational tools needed to design low-boom aircraft. It validated those tools through wind tunnel testing and flight experiments. It created a knowledge base that would enable future efforts. When technology advanced further, when computational power increased, when new approaches to airframe design emerged, researchers would have a solid foundation to build upon. The researchers who worked on the HSR program's sonic boom element made contributions that will influence aerospace engineering for decades to come. Christine Darden, Robert Mack, Peter Cohen, Ed Herring, and many others advanced the state-of-the-art significantly. The students who worked on HSR-related projects in universities across the country gained experience that shaped their careers. The technical reports, journal articles, and conference papers produced during the program documented knowledge that won't be lost. The dream of quiet supersonic flight persists. The X-59 low-boom flight demonstrator represents the latest attempt to realize that dream. It builds directly on work done during the HSR program. The theories, the computational methods, the design approaches, the testing techniques, all trace their lineage through HSR back to earlier programs. Each generation of researchers builds on the work of predecessors, gradually pushing the boundaries of what's possible. The story of sonic boom research in the 1990s reminds us that scientific and engineering progress is rarely linear. There are advances and retreats, periods of intensive effort and times of reduced activity, successes and disappointments. The HSR program had all of these, but the overall trajectory was forward. We understand sonic booms far better now than we did in 1990. We have better tools for predicting and potentially controlling them. We have a clearer understanding of what would be required to make quiet supersonic flight a reality. The challenges that defeated the HSR program's ambitions for overland supersonic flight haven't disappeared. Sonic booms are still loud. People still find them annoying. The performance penalties for low-boom designs are still real, but none of these challenges are absolute barriers. They're engineering problems, difficult but potentially solvable. Future researchers armed with better tools and standing on the shoulders of HSR program veterans may yet find solutions. Thank you for joining me on this journey through one of the most ambitious aerospace research programs of the late 20th century. If you enjoyed this deep dive into the technical challenges and human stories of sonic boom research, please consider liking this video and subscribing to Space Historian. There are more stories to tell about humanity's quest to push the boundaries of flight, and I look forward to sharing them with you. Until next time, keep looking up and keep wondering about the possibilities that tomorrow's technology might bring.